Hello everyone, welcome to Math 1720D Calculus 2. This is the first day of class, so let's review some Calculus 1 materials. And we're going to begin with antiderivative formulae. Here are the three most elementary formulae: power function, and special case, reciprocal function, and exponential function. Power function is the easiest and actually the most important too. Add the power by 1 and then divide. That's precisely the opposite of differentiation, which was multiply the power and subtracting 1 from the power. Of course, that doesn't make any sense when k is equal to -1 because denominator will become 0 here. In that case, we have the next formula down here. This x to the negative first power is the same as 1 over x function, so the antiderivative of that is logarithmic function. Now, why do we have absolute value here? That's because inside of the logarithmic function has to be strictly positive. So absolute value, make sure you make it positive. Indeed, you can check the right hand side by taking the derivative. Take the derivative of log function and you get 1 over x. Good. Take the derivative of log of negative x, you have again 1 over x. And this is when x is positive. That's when x is negative and forced into positive by taking the absolute value. The third one is an exponential function. Exponential function, of course, stays the same. However, those are not really useful. These three are more useful. These are three elementary antiderivative formulae combined with elementary chain rule. The same goes here. Add 1 to the power and divide. However, the derivative of the inside is a linear function, ax plus b, and we have to divide by a in order to undo the effect of chain rule. What do I mean by that? Let's start from the right hand side. Start from here and then take the derivative of this function. What happens? K plus 1 times this, and then we have to subtract 1 from the power. So that's the derivative of the outer function. But that's not all. By chain rule, we have to multiply the derivative of the inside. And what do we have to multiply? We have to multiply by a. That's the derivative of the inside. In order to undo this multiplication, we begin with this coefficient, 1 over a times k plus 1. Consequently, this k plus 1 and that k plus 1 cancel out, and this a in denominator and that a in numerator cancel out, and we only get, well, precisely what we wanted, the integrand. Consequently, we have this 1 over a in all these formulae. Again, the same deal. We are just undoing the chain rule. 1 over a is a recurring theme for log function, exponential function, and later on trigonometric functions too, as I'm going to show right now. And here they are. Here are the antiderivative formulae for trigonometric functions. Derivative of sine is cosine, so antiderivative of cosine is sine. Vice versa. Derivative of cosine is negative sine, so antiderivative of sine is negative cosine. However, we need this 1 over a in order to undo the chain rule. Here, there, everywhere. Okay, remember these formulae. I hope everybody memorized all these, but even if you do not, please make sure they are handy so that you can look up very quickly. Actually, if you do a lot of homeworks, not a lot of homework actually, just even the minimal required homeworks will be sufficient to make you memorize all these just naturally. Here's some more trigonometric formulae, not as important, so I did not make a box with it. Excuse me. But here they are. Antiderivative of tangent is log of secant. Antiderivative of cotangent is negative log of cosecant. It could have been written in some different fashion, kind of like this: negative log of cosine or log of sine, but This is the way it is written in the back of our textbook, and a little bit more standard too. And how do we derive this? One way is to start from the right hand side and take the derivative and then force it into the integrand, and that's the easiest way. Another way is to use substitution. Tangent is sine of a cosine, and you simply take, say, u is the denominator, cosine, and use substitution, and you'll be able to deduce this formula in the right hand side. I'm going to leave those to you because it was well covered in Calculus 1. Here are a couple other formulae, and these are so complicated that I don't even remember, as a matter of fact. Whenever I have to do some secant and cosecant, I just look up, and here they are. So I de-emphasize with a little bit lighter gray. That's what I mean by in this notebook. Black, important. Light gray, not that important. And boxed, even more important. Here's some more squared trigonometric functions, and these show up a lot in Calculus 2. Sine squared, cosine squared, tangent squared, cotangent squared, and then here are the formulae, but not just formulae, but I want you to be able to derive these as well, to tell the truth. How do we do that? We use a trig identity. Sine squared of x is equal to 1 minus cosine of 2x over 2. And this formula is sometimes called double angle formula, sometimes called half angle formula, so it's kind of confusing. So I usually call it power reduction formula. So reduce the power 2 to 1, and then we can apply the antiderivative formula that we discussed in 2.1, and here we go. You can do the same thing to cosine squared function. Again, by power reduction formula and some further computation, we have the answer. How about these? These two are related to Pythagorean identities. What is tangent squared? It is secant squared minus 1. As a matter of fact, it comes from like this: sine squared of x plus cosine squared of x is equal to 1. That's coming from the Pythagorean identity. Divide everything by cosine squared. What do you get? Sine squared of x divided by cosine squared of x plus 1 is equal to 1 over cosine squared of x. And what is sine over cosine? That's tangent, isn't it? Is equal to, what is 1 over cosine? That's secant. And we can easily deduce the Pythagorean identity for tangent and secant starting from the standard one. Sine squared plus cosine squared is equal to 1. That way you can reduce the number of formulae that you'll have to memorize. But if you're uncomfortable with deducing things like these, then it's okay to memorize or write them in the formulae table and then keep them handy. In any case, if you have tangent squared, you can rewrite it into secant squared minus 1. And please recall that antiderivative of secant squared is well known. That's tangent. Antiderivative of 1, that's just x, and that's how we get this formula. You can do the same thing to cosine squared function. You can start from Pythagorean identity, sine squared plus cosine squared is equal to 1, and divide everything by sine squared, and you're going to get the relation between cotangent and cosecant. Here's some more inverse trigonometric function formulae. Here they are, and I don't know whether you remember all those inverse trigonometric functions derivative formulae or not. They come from inverse function formulae or implicit differentiation. Either way you can deduce them. I generally prefer implicit differentiation. But in any case, derivative of arcsine is 1 over 1 minus x squared. Derivative of arctangent is 1 over 1 plus x squared. And derivative of arcsecant is 1 over x square root of x squared minus 1. And then here we are, because of those a inside, we have those recurring theme of this 1 over a, but not always, so these are kind of tricky. How important are these inverse trigonometric functions, antiderivative formulae? Not much, to tell the truth. The only thing that is somewhat worthy is, arctangent one, because that's related to quadratic irreducible factors of the denominators of rational functions. Am I making sense? Well, we're going to talk about it several sections later. Okay, let's move on to the next topic, integration by substitution. And it was kind of like this. Basically, it was reverse chain rule. What is a chain rule? Here we go. Everybody should remember that, right? Derivative of a composite function, we have three rules. Number one, derivative of outer function first. Number two, inside stays the same. And number three, derivative of the inside is multiplied outside of all that. That's a chain rule. Okay, I don't think it is necessary to go over to example problems. That's way too easy. And how do we reverse the chain rule? Well, it kind of goes like this if you can follow. And we end up with substitution, y becoming the inside part. If you used u substitution most of the time in Calculus 1, please get used to some other characters here, because I'm going to use u's and v's mostly for integration by part. So for substitution, I'll generally use some other character. I'm going to use y a lot. And for criteria, here we go. Is that a composite function? And then the derivative of the inside should be flying around somewhere. Okay, and then here is the process, but it makes little sense unless you actually have some problem with you. So let's go ahead with a problem set. Let's see, for example, how about a problem like this one? Okay, here's a good problem. Let's see, just a moment please. Okay, I paused the video a bit and then created an auxiliary window right over here, and I copied the problem down here. And here we go. The step 0 is the recognition. That wasn't too much of a problem in Calculus 1, but in Calc 2, because there are other techniques that you'll have to use, the recognition is important. Recognition, there are two things to remember. Number one, do we have a composite function? Yes, we have a power function. This fifth root is a power function, power of 1/5 power, and we have a function inside. And what is the derivative of that function? 2x. Modulo constant coefficient, the x is showing up. So we have both criteria correct. And then what do? Step 1 is substitution. We take y as the inside, kind of like this. Y as inside, 16 plus x squared, like that. And then step 2, take the derivative. dy dx, right hand side is 2x. Step 3, solve for dx. Solve for dx. dx equals 1/2x times dy, kind of like that. I color-coded into red and blue respectively so that I can see things better when you do second substitution at step 4. Let's substitute these into the original integral, and what happens? The 16 plus x squared, the red part, will be substituted by y, which I color-coded as red. And the other part, this dx, which highlighted in blue, will be substituted by 1/2x times dy, kind of like that. Do you see a cancellation? Normally you will. X cancel out, and what do we have? We have a y integral here. So this is nothing more than y to the 1/5 power, so we can calculate the antiderivative using the power rule. Add 1 to the power and then divide, and then here's the antiderivative. And this is correct antiderivative, yes, but not correct answer yet, because the original problem was given in terms of x, and this answer, correct answer, yes, but it is given in terms of y. So let's go over to final substitution. Step 6, plug in y equal to 16 plus x squared back in, and that's the final answer. That is a standard way to do substitution. So more substitutions are possible, of course, but that review is left to the students. After all these were covered in Calc 1.